Namaste. All right, guys, I just wanted to do a really quick video just outlining some, just to augment the screencast 5 video that I did for you guys on gravity. First, what I wanted to say, so starting with Isaac Newton's equation. Now, again, gravity is important in terms of general knowledge, all right, just because one, we really kind of need it. Our bodies respond to it, and if we are outside of gravity too long, our bodies atrophy. Not that you're going to be outside of gravity too long, like who really is. At some point, though, very serious discussion, okay, about your generation or future generations. We need to leave the planet or we die. And your generation or your kids, towards the end of this century, maybe sooner, maybe later, but we'll probably start in a very serious way to leave this place. We're getting the technology now and also the need where we might actually have to leave. Why? Because we're starting to use up our resources, all right? There's only so much metal in the Earth's crust. Where are we going to get more iron when we run out of iron? Okay, well, it's everything on the Earth is actually out in space. Especially there's enough material in the asteroid belt. The statistic goes like this, that there's enough material in the asteroid belt between the planets Mars and Jupiter to build a skyscraper around this whole planet, something like 800 stories high, and that's a fact. Why would you ever want to do it? You wouldn't. The point stands, though, that whatever we need is out there, and just like we have done in the past, where we have gone places to go and get things, our own country included, right? When the Europeans spread out throughout the world to go get stuff, all right, we'll probably do that, okay? And this will become very relevant at some point in the future, all right? So anyway, force of gravity, according to Isaac Newton, is you have a gravitational constant. It's proportional to the two masses that are in question, like a moon and a planet, or a planet and the sun, or something, and it's inversely proportional to the square of the distance between them, okay? Now, like I said in the other video, this is also because the force of gravity on you is called what we call your weight. And when you're on the Earth's surface, that's equal to m times g. And so this m would be one of the m's here. So one of the other m would be like the mass of the Earth that's creating gravity. And then this r would be the radius of the Earth. All right? And so this m would go with one of those m's there, and we get the expression g. 9.8 is gravitational constant, me, mass of the Earth, divided by the radius of the Earth squared. And sure enough, that does actually work out to be 9.8 and confirm what Galileo measured 500 years ago. So it actually does work out. So the other thing I wanted to make a connection with was that the potential energy expression is mg and h. Well, I already said that g is equal to the gravitational constant, mass of the Earth, divided by the radius of the Earth squared. So when I take this and I put that substitute in there, I get that potential energy is your mass times, instead of little g, big G, mass of the Earth, radius of the Earth squared. Now instead of h, because h is essentially, even if you're even if you're on a very tall building, compared to the 4,000 mile radius of the Earth, you're still basically right on top of the Earth. H is approximately the radius of the Earth. And here's what I mean by that. So if this is the Earth, from here to here is 4,000 miles. That's twice the distance from here to Florida. Even if you are in a low orbit satellite, 200 miles high to 400 miles high, you're still right there. you are not off the Earth. And that just shows you how thin our atmosphere is also. Like the atmosphere is not like this big, huge ocean of air. It's not. It doesn't have a big, it's this thin little veil of gas around this planet. And so point being is whatever height you're at you're still pretty much the radius of the Earth. All right. So instead of H, I'm going to write RE. And that gives me a potential energy equation of that cancels with one of the R's down there. And that gives me a potential energy equation of mg me over RE. And that's what U is. That's another way of writing it. And let me give you some more board space there. So there you have it. Now, what does this have to do with anything? Well, here's a connection with space here. All right. And I just want you to follow me. Okay. I'm going to leave this down here. I'm going to erase this. So let's say here we are on the Earth, okay? And get theoretical with me for a second, and we're going to launch a rocket, okay? Now on the Earth, so we're going to launch a rocket from the Earth, okay? And as the rocket is moving, it has some energy. It has some kinetic energy, 1/2 mv squared. By the fact that it's even on the surface of the Earth, it has potential energy. Why? Because on the surface of the Earth, it's still not in the center of the Earth. Okay, so it has some potential energy just being on the surface of the Earth, away from the center of mass, 4,000 miles away from it. It's kind of significant. So it's got some, so if you make the 0 point for potential energy, the actual center of the planet, the potential energy that the rocket has sitting on the launch pad is this right here. It's the mass of the rocket, okay? Mass of the Earth divided by the big G in there, divided by the radius of the Earth. Now, let's say we do this. So the rocket launches and then goes out in space and then coasts farther and farther away. We say gravity has an infinite range. That means it extends, as far as we know, forever. Now, at a certain point, it's so weak, the Earth's gravity is so weak, that it's not pulling you back, okay? So let's say that the rocket, but where is the Earth's gravity? Where does it stop to pull a rocket? Pulling the rocket at infinity. At infinity, the force of gravity, okay, because remember, forces do work. They change energy, okay? The force of gravity would have taken away all of this energy that the rocket had, we say, at this distance of infinity. So at infinity, all right, the energy the rocket has, its energy change is 0, okay? So we can set this expression equal to 0 because the force of gravity would have done work on it and have taken this energy away. So so due to conservation of energy, we can say that. So just kind of bear with me where I'm going with this for a second. So I can say that 1/2 mv squared of the rocket plus me big G over RE is equal to 0. Well, so what? Well, that means that, well, one, the m's go, because you can divide the mass of the rocket out, okay, on both sides. And I'm given this expression, 1/2 v squared, okay, still got room there, all right, is plus the mass of the Earth, G, big G, RE equals 0. What does that mean? It means 1/2 v squared is equal to, just take this and put that over there. It means that these two terms are equal to each other, is equal to the mass of the Earth, big G, radius of the Earth, okay? And so we'll take the absolute value there, okay? So, the negative sign doesn't really factor in too much here. What does that mean? Well, if I solve for this V, okay, V is equal to big square root sign, okay? Get rid of that. Bring that 2 up here. 2 big G mass of the Earth over the radius of the Earth. What does that mean? That means that this velocity if that the rocket has at the beginning winds up being zero energy at infinity, that particular velocity is the escape velocity. So know that. Okay? So escape velocity. And what is escape velocity? Well, you're always taught when you're a little kid that that what goes up must come down. That's not true. If you throw something up fast enough, it won't come down. If you throw something up at least that velocity or faster, it will never come down again. The Earth's gravity will get so weak that it will never be able to pull it back down. All right. What is the escape velocity for the Earth? It's something like 22,000 miles an hour. It's about 7 miles a second, which is how fast those astronauts, when we shot astronauts to the moon, they had to achieve escape velocity. So which is actually much, much faster than a bullet from a gun, which is just immensely impressive to me that in order that we actually made people go much faster than a bullet out of a gun. 7 miles every second is about how fast the Earth's escape velocity is. If you wanted to know what the escape velocity was for any other planet, let's say Mars, instead of the mass of the Earth, you would put in the mass of Mars and you would put in the radius of Mars, or whatever planet or moon that you're talking about. Okay, so anyway, that's a little bit trying to clear you guys up a little bit about potential energy, and also this new concept that is a direct result of thinking about energy in this new way of escape velocity. All right, okay, pull this out.